Also, apologies to anyone who might have heard a version of this before. Some of you, for some of you, there will be slightly sharper results. Also, I try to put the stresses on a bit differently. In particular, there will be full proofs with full details. Okay, so evaluations already appeared in this conference, so I'll be quick. We will be working with complex quantum sets, non-empty ones. We topologize them with the Hausdorff distance. And evaluation is a map that satisfies the inclusion-exclusion principle whenever there's two convex bodies such that their union is also convex. We want this relation to hold, as you would expect from a finitely additive measure. Okay, and particularly we will restrict our attention to the convex relations, which are, in addition to being relations, are translation-invariant and are continuous with respect to the Hausdorff distance. Here are some examples. The Lebesgue measure, of course, is a relation. Also, the constant relation is a relation. I will be calling it the Euler characteristic for a good reason, but of course the Euler characteristic of a convex body is 1 constant. Surface area is a good example of evaluation which is not a measure. And the intrinsic volumes, they have all been appeared at least three past talks. Are good examples of relations. They can be defined through Steiner's tube formula. Namely, you look at the epsilon tube around the convex body. This is a polynomial in epsilon, and the coefficients properly normalized are functions of k, and they are relations. Moreover, they are relations that are invariant under the orthogonal group. Okay, so the simple examples are the Euler characteristic, surface area, and the volume. Okay, some key facts that we will be making use of are this. We will be looking at J-homogeneous relations, which are what you know they are. And the J-homogeneous relations are denoted like so. We will also be looking at even and odd relations, which are given by this equation. And the key observation of Macmillan is that the space of all relations is a direct sum of homogeneous relations with degree of homogeneity being an integer between 0 and n. So it's usually enough to restrict your attention to just one of those spaces. The examples are zero homogeneous relations are one-dimensional, spanned by the constant relation. Hadwiger noticed that the n-homogeneous relations are also one-dimensional space spanned by the volume. All the other spaces are infinite dimensional. They're interesting to study. They have many interesting properties. And particularly, we will preoccupy ourselves with smooth relations. What are smooth relations? They were introduced by Alesker 4 years ago. That's a relation such that if you look at this orbit map, the one that to linear transformation assigns this relation, composing with this map is smooth. Okay, so we will denote the space of smooth relations like so, with an infinity, like functions, and that's a general important fact. They are dense subspace with respect to a certain topology that they have not defined here. Here are some examples to keep in mind. The intrinsic volumes, they are smooth, while something which is like this relation, the volume of a projection to a subspace, this is not smooth, and here you can see why. When you rotate an interval, you will be passing through 0 at some point, and this function will be behaving like an absolute value. This is not smooth. Good. Why do we look at smooth relations? There's some motivation for that. Here are three reasons that I distilled. A lot of relations that appear in nature, somehow they are already smooth. As a space, it has very nice algebraic properties. There are various structures, in particular the Alesker product, which is only defined on smooth relations, at least a priori. Those structures are closely related to integral geometry, to kinematic formulas. Perhaps most importantly for us today, the smooth valuations, they somehow paved the way to consider valuations on smooth manifolds. So they can be naturally evaluated on all kinds of sets, not just convex bodies, but for instance submanifolds with corners. And so it gives a natural definition, which will later appear, of valuations on manifolds, where the notion of convexity does not make sense. All right, so here it is. We have a manifold of capital M of dimension little m. And I will be assuming for simplicity that this manifold is Riemannian, is equipped to some of the Riemannian structure, that it is oriented. Those things are not important, but it will make life easier for us. And we need to choose a family of test bodies. It will be denoted like so. It will be replacing the space of convex sets in a linear space. So we will be choosing compact submanifolds with corners. That's not the only choice you can make, but the choice doesn't really matter. What's important is that those sets have a normal cycle. What is a normal cycle? This is the normal cycle of X is a subset of the sphere bundle. So on the picture, it looks like so. You just take all the unit vectors that point out of your set at an angle of 90 degrees at the smooth points, or the normal cone, the union of the normal cones to your set. And this normal cycle has some nice properties. It's a Lipschitz submanifold, and it has the same dimension, m-1, regardless of the dimension of X. So that's a bit confusing maybe at first, but then you realize that if X has smaller dimensions somewhere, it will have more orthogonal directions, and the sum is always the same. It's m-1 dimensions. Okay, so we have the normal cycle. And here comes a definition, which goes back to Alesker and so evaluation on a smooth evaluation on a manifold is a function on test bodies, which is given by a pair of differential forms, omega and mu. Omega is an m-1 form on the sphere bundle, mu is a smooth measure on the manifold, and the evaluation is given by this formula. It has the inner term, which is just a measure. It's a boring thing, but we need it if we want to include measures. And this is the interesting part, the boundary term, integrating the fixed form omega over the normal cycle of X. The justification for those definitions, one justification is that if you look at the manifold, which is the linear space therein, and then you look at all the translation-invariant elements there, this is in a natural isomorphism to the space of smooth valuations that was introduced earlier. So that really is an extension of the notion of valuation. Okay. So on manifolds we also have intrinsic volumes. They in a way they will serve as a motivation for us. So let me recall the definition. It comes from Weil's theorem, Weil's cube formula. Here is a reformulation of this theorem in the language of valuation theory. Which is due to Alesker. We have an embedding of manifold M into some large dimensional Euclidean space, an isometric embedding, and M is a Riemannian manifold. Okay, then we can take the intrinsic volumes mu I of Rn and we restrict them to our embedded manifold, which is just to say from now on we just evaluate those intrinsic volumes of subsets of the manifold, and by some general theory we get evaluation on the manifold. And the key observation, the statement is that those valuations are independent of the choice of isometric embedding. They only depend on the Riemannian structure on the manifold, or in more classical language, they depend on the first fundamental form, but not on the second fundamental form of this embedded manifold. Great. So those induced valuations, they're called the intrinsic volumes, or the Lipschitz scaling valuations. They're called so, for instance, because the measure part of them are just the classical Lipschitz scaling curvatures, which are some polynomials in the Riemannian curvature tensor. Great. And here the examples are the volume. This time the other characteristic really is the right way to call this valuation mu0, because it is the characteristic. And the m minus second one is proportional, evaluated on the whole manifold. It's just the integral of the scalar curvature. Okay, finally we arrive to the topic of my talk, really. So, like the previous talk, it will be about extension problems for evaluations. So, let's recall a classical, very important, very exciting theorem of Nash. That says that if you have a Riemannian manifold, then you can embed it isometrically into some Euclidean space. So, inspired by all of that, we want to ask the same question for evaluations. So here's the question. We start with a smooth evaluation on a manifold. We defined it already, this object. Can we find an embedding into some linear space and the translation invariant smooth evaluation capital phi on that space, such that the given evaluation is the restriction of the translation invariant evaluation? So first you notice there is an obvious abstraction here. For instance, if you are the restriction of a translation invariant evaluation, this little phi, you can evaluate it on such test sets, which are just singletons. And if it's the restriction of something that's translation invariant, it's going to be independent of the choice of points. Okay, so that's an obvious restriction. This function must be constant. The theorem, which I forgot to say, everything I'm presenting is joint work with Georg Hofstaetter. The theorem is that this is the only abstraction. So here is the, and in fact something much stronger holds. So there is an embedding into some large linear space such that the image of the restriction map is precisely those relations which are constant on singletons. This is, by the way, not a very big restriction on in evaluation. Basically, the quotient of all evaluations by this space is just the smooth functions. It's not a big difference in a way. So not only can we find an extension, an embedding that's good for any given evaluation, but we can find an embedding that's good for all evaluations at the same time. And that's actually important because, for instance, it allows you to talk about Alesker product of the evaluations and at the same time on the space and on the submanifold. And even something stronger holds that not only
is isometric.
I'm sorry?
It's an isometric embedding?
There's no metric involved.
So but you can ask the question also for an isometric embedding.
Well, but there's no metric involved. So I'm not sure what you're saying.
If you start with a Riemannian embedding, you could want a Nash embedding that also...
Sure, but they don't have a Riemannian manifold.
I thought you said you did, but okay.
So the only reason I said in the beginning Riemannian manifold is so that they can talk about the sphere bundle instead of projectivized cotangent bundle, but it really didn't. I never used any Riemannian structure for anything. For anything important. Okay, so moreover, a generic embedding into a linear space, which has sufficiently large dimensions, will do. So this is my claim of relevance of this stuff to this workshop. The large dimension plays a role. Okay, if you, to be a little bit more precise, so this an embedding would be good for this result whenever this map, which takes a tangent line to the manifold and just forgets where it was tangent, so it's just a line in the linear space now, whenever this map is an embedding of smooth manifolds. We call such embeddings perfectly non-parallel. Great, so we have a Nash theorem, and here is a framework for this kind of problems. We will be seeing another instance of that soon. The framework is of Whitney extension problem. So we will be looking at some families of subspaces as in Rn, and we will have some data. So for every E in S, we have a smooth valuation on E, which is J homogeneous. And we are assuming compatibility, as you would, whenever two subspaces intersect, the corresponding restrictions to this intersection should coincide. And we don't want any silly abstractions, so whenever it makes sense, we require this assignment to be smooth. So this makes sense, for instance, when S is some manifold in the Grassmannian, some smooth family of subspaces. So the question we want to answer is, can you find a globally defined smooth valuation with the assigned prescribed restrictions, little by e? So the Nash problem, the Nash theorem, really easily reduces to this Whitney problem, where S is just the family of tangent subspaces to M. So if you choose some embedding of M, then it immediately reduces to this Whitney problem. And then if you're careful to choose an embedding such that no two subspaces intersect, which can be done if the dimension is high enough, then there's no compatibility issues. So you might be expecting to have a positive solution to the Whitney problem. And under the slightly stronger assumption of this embedding property I was talking about earlier, perfectly non-parallel, we indeed get a positive solution to this Whitney extension problem. So what can I expect with respect to time?
You have half an hour, right?
I don't know.
Yes.
Yeah, so it's 20 minutes.
Okay, thank you. As an application of the Nash theorem, let me say a couple of words about Crofton formulas. So in linear space, there is a very nice description of valuations through Crofton formulas, which goes back to Alesker's irreducibility theorem. The description is as follows. So if you start with the fine Grassmannian of a certain dimension, and you look at smooth measures on the fine Grassmannian, which are invariant to translations, then you can write a Crofton formula, which will give you a smooth given J homogeneous solution. The formula is: take your set, intersect it with the subspace, write 1 if they intersect and 0 if they don't intersect, you get a function on the Grassmannian, integrate it with respect to the measure with which you started. That's a valuation. Alesker's irreducibility theorem implies that this map is onto, that any smooth valuation, even smooth valuation, has such a description. And in fact, you can also have a similar description for odd valuations, except you need to be using half spaces instead of spaces, and there are some technical aspects that I don't want to discuss. But okay, we have Crofton descriptions of relations, and there was a question that was, for instance, asked by Georg whether you can do something similar on smooth manifolds. So on a smooth manifold, ideally you would have some nice family of submanifolds. So who particularly fantasized about one manifold A, which is carried around by a smooth family of diffeomorphisms, and there will be some measure for this family of diffeomorphisms, such that any evaluation can be written in such a way. So the motivation behind Fo's question is that there is a product structure on smooth evaluations which is closely related to intersection of sets. So non-formally, one can say that if you look at this evaluation and that evaluation, their product should be the Euler characteristic, intersect those two sets. Right. And so if you think about this kind of basic building blocks for evaluations, the product becomes very easy to define, very natural, and very obviously related to integral geometry. But in practice, the product in relations is defined by complicated formulas, So having such a description would allow to have a natural description of the product. Okay, so that hopefully that motivates the quest for Crofton formulas. And so the Nash theorem allows to get something of this sort, although not as perfect as Georg was hoping for, maybe. Basically, what you do, you present your evaluation as the restriction of a translation-invariant evaluation. The translation which you can do up to this function thing. So the translation-invariant evaluation has a Crofton description. Then you just take the family of subspaces or half-spaces you have there. You intersect them with your submanifold. You get some family, singular, but some family. And to account for the function, you also take balls of various radii, intersect them also with your submanifold, and in this way you can get an evaluation as a Crofton, slightly singular, but nevertheless Crofton formula. Okay, so now I'll breathe. And I'll talk about another type of Whitney extension problem for evaluations for finite subspace arrangements. So we'll need a couple of definitions. So we'll be talking about finite collections of subspaces, and there will be no restriction to the dimension. They could be of different dimensions. Here's the definition. We will call an arrangement of linear subspaces minimally intersecting if for any subset of this collection, the codimension of the intersection is the sum of the codimensions. So this is what you expect of a generic intersection, but not quite, because for instance, if you have two lines in R3, then generically they intersect at a zero-dimensional space, not a -1-dimensional space. So minimally intersecting somehow means that they're still intersecting. That the ambient space is not too large for it. That's the definition. And we will be saying that S is semi-generic if whenever you have a subset of subspaces that intersect non-trivially, this collection is minimally intersecting inside their span, their sum. Okay, so this is slightly more general than being a generic family. So here are some examples. For instance, if you have up to n hyperplanes in general position, then they are minimally intersecting. Any two subspaces are semi-generic. A nice exercise in linear algebra. Also, three non-intersecting subspaces are semi-generic. And the last sentence here says that if you take subspaces in general position, they will be semi-generic. Okay, So some condition. And here are two theorems that we can prove. Both of them talk about semi-generic arrangements of proper subspaces over M. So S here, this S stands for small, I guess. I will try to explain later why. But here is the theorem. So we have some such collection. And we have the condition that whenever we have J plus 1 subspaces there, their intersection is at most J minus 1 dimensional. All right. Because this is an inequality, it's an upper bound on the dimension of the intersection. We think about it as a condition of small intersections. Okay. And then I claim that the Whitney problem can be solved. What does it mean? Explicitly, if we have a valuation phi e on every e, a J homogeneous one, such that any two such valuations coincide on intersections, then you can find a globally defined valuation with those prescribed restrictions. Curiously, if J is at least n over 2, this condition here is satisfied automatically. I mean, look at it. It requires, as J increases, it requires less things. It says, okay, now you look at larger spaces, so their intersection should be smaller, but then it requires that their intersection is bounded by a larger number. So it's kind of make it much easier as J increases, and once J passes on over 2, this condition is just satisfied. So this theorem says in particular that for any semi-generic set, if the degree of homogeneity is at least n over 2, you can extend from any compatible collection. That's a bit surprising. The other theorem is kind of complementing. So here the condition is whenever you have a subset of 2J plus 2 subspaces, they must be minimally intersecting. So that's a very bad terminology, but it somehow means that their intersection is large. While being generic, it's large within the ambient space. So with this condition, again, the Whitney problem, the same problem, would have a solution. As a corollary, if you look at the family of hyperplanes in general position, the Whitney problem has a solution if J is not n minus 1 over 2. So for J great at least n over 2, that's the previous theorem. And for J which is less than less or equal n minus 2 over 2, it can easily be checked to satisfy this condition. And one dimension that's accepted is n minus 1 over 2. And curiously, the theorem fails here. So we have a counterexample, not a very hard one, in dimension 3. So it points to some sharpness, I guess, of the result, even though sharpness could mean different things. Okay. So I have what? 8 minutes?
Yes.
Thank you. So I can say a few words about the proofs. Before the proofs, what are the challenges? There are a few. One challenge is that the operation of restrictions of valuations, in particular for restriction of valuations on manifolds, is a bit hard to describe. So recall that the valuation is given by some differential form. You're integrating a differential form omega over the normal cycle. Now, if you have a valuation on a larger space and you want to restrict it to this plane, what would it mean for the form? So you need to consider the normal cycle of this amoeba here in the plane and also in the larger space. So the black arrows are the normal cycle in the plane, the red arrows are the normal cycle in the larger space, and the operation of restriction would correspond to integrating along this half sphere. So once again, to reiterate, the operation of restriction of valuations correspond to some integral operator on differential forms, and that's harder to work with. Okay, that's one issue. Another issue is that this presentation of evaluations by a pair of forms is not unique. That means that if you have compatibility of evaluations, it doesn't mean that the corresponding forms would coincide. This problem has a natural solution. So the kernel of this assignment that takes omega and mu and gives you phi, so this ambiguity in the choice of omega and mu is well understood. There is a theorem of Wernicke and Peuker that describes this ambiguity precisely. Basically, it says that we should be looking at the Riemann differential of those forms, and then it's a unique description. Okay, but then we would need to be interpolating our forms within this space, and once again, that's a bit challenging. Okay, so those were the difficulties, and now I can tell you something about the tools that go into the proof. So one thing we have at our disposal, luckily, is the Alesker Fourier transform, which interchanges restrictions of evaluations with another operation, which is called push forward of evaluations, and while it's a bit less intuitive to describe geometrically on the level of differential forms, it corresponds precisely to restrictions. So the formula for push forward is basically like that. You take a product with some body in the complementing dimension, and you shrink it to 0, and you take some derivative. That's a description, and somehow it's clear that the only arrows that participate are the ones that already point in the dimension of your target subspace. Okay, so we can apply this Fourier transform, pass to push forwards, and one problem goes away. Very good. Okay, so now I want to describe in give more or less complete proof of the Nash theorem. It will take just 2 slides. So and 5 minutes. So like we were saying before, the problem immediately reduces to the following problem. We have a field of translation-invariant valuations over all the tangent spaces of M, K homogeneous translation-invariant valuations, and we want to find one globally defined K homogeneous valuation with those given restrictions. We want to show that this map is onto. The first thing to consider is the case of K equal to 1. So here we need to consider even and odd valuations separately. So for even valuations, one homogeneous even valuations, it's well known that such evaluation is in one-to-one correspondence to functions on projective space. Basically, if you restrict such evaluation to a line, you get a two-type measure on the line. You can think of it as a function, like a number on this line. Two-type measure is described by a number, and any such function would correspond uniquely to evaluation. So basically, if you look at those Klein, they are called Klein functions. You would be given some Klein function on some subset of this projective space that comes from all the lines that are tangent to M. And if you chose your embedding well, there should be no problem extending it smoothly somehow, and that would be some valuation. So that was easy. Good. For odd valuations, it's a bit trickier. You need to do a Fourier transform and think a little bit, but it basically reduces to the same thing. So one homogeneous case is easy. And here comes the upshot. We can capitalize on that to prove for every key. We will be using the Alesker product for it. So while I kind of defined it even, but we don't really need to know the definition. What we need to know is that it's a natural operation which commutes with restrictions. Okay, and so here is the basic diagram. We want to show that this map here is onto, from valuations everywhere to valuations on the tangent, well, field of valuations on the tangent space. So there is Alesker's irreducibility theorem, which basically tells you that whenever you have a natural map whose image is inside a space of valuations, this map would be onto or 0. Okay, so here we have this Alesker product from the k tensor power of the one homogeneous relations to the k homogeneous relations. So this map must be onto. We have a similar map which takes product in every tangent space. This map is onto. This is due to same set property, Alesker's irreducibility, and also a nice property of smooth relations, the property of nuclearity. I'm not going to define it, it comes from functional analysis, but it has very nice properties when you're working with tensor products, as we do here. In particular, it implies that this map is onto. We also have this map, which is basically the restriction map for one homogeneous relations, which we extended to the k tensor power. Again, using nuclearity, this map would be onto. And to reiterate what we're doing, we started with something here, we find the preimage here because it's onto. We find the preimage here because it's onto by the case of k equals 1. And nuclearity, and now we go the other way, and we found something here, which is mapped to what we started. So we proved the Nash theorem, and this is great. For finite arrangements, I have 1 minute. I am inclined to tell it. Is it okay?
Yes.
Thank you. So basically, it's a complicated proof, but there are just two basic building blocks which are kind of simple to explain, at least non-formally, so I will try to do it. The first is actually a formal claim. So if you have a semi-generic collection of subspaces in Rn, and some smooth functions on the corresponding spheres in Rn, which coincide on the intersections, then it's a nice exercise to show that there is a globally defined smooth function with those restrictions. The other claim is like this. We have some forms which are, I'm being here informal, I'm sorry, there's only one way to say it, and it's the informal way. So you have some forms defined over those spheres, and you know that their differentials coincide over the intersections. What we do, we prove that they can be replaced with forms at I prime, such that on the one hand, the difference is closed, so it would not be affecting the corresponding relation. On the other hand, such that the compatibility happens not for the differentials, but for the forms themselves, which we later can interpolate. And, well, that can be done. I will skip the open question. Well, no, I will not skip it. It's short. So, with the problems, that's kind of just the beginning. You can ask many different questions. You can ask it for continuous relations. You can ask for all kinds of families, not just finite arrangements, but some interesting submanifolds of the Grassmannian. You can impose some conditions like positivity and monotonicity, and ask if you can interpolate within this class. I think those questions are very natural and interesting, and we don't know how to answer any of them. And that's that. Thank you very much.